Few basic points related to satellite link. Let me read all these points first. All the microwave range cannot be useful for satellite communication. Only certain windows are used where the attenuation are minimum. This is the attenuation plot of the atmosphere with frequency. As you can see, below 20 gigahertz, the attenuation is very low. But above 20 gigahertz, the attenuation is showing some uneven jumps, right? Here we have some high attenuation, then we have some dip, then again near 60 gigahertz we have very high attenuation. After that there is a dip or valley region. So these regions where the attenuations are lower are actually useful for satellite communication. And at the same time, as you can see, as the frequency is increasing, the overall attenuation is also increasing, right? So here the valley is right here, the valley is right here. So this valley attenuation at this valley is higher compared to this one, right? Similarly, as you going on increasing the frequency, the valley region is also going in the upward direction. That means at the higher attenuation region. Okay. Also, these peak values can never be used for the satellite communication system, ground station to satellite communication system. This particular frequency ranges or this range cannot be used because it is showing very high attenuation characteristics. But what is the utility of these particular frequencies? Actually, these frequencies are very much useful for remote sensing purpose because the atmospheric perturbation is highest at these points. So obviously, if we use these frequencies, these peak frequencies, then we will get more information related to the atmosphere. So those frequencies are useful for remote sensing, but they are not. These frequencies are not suitable for satellite communication. For satellite communication, we have to find those windows. These small valleys are actually called the windows. So we have to use the windows. Major bands used in satellite system are 6 by 4 gigahertz, 14 by 11 gigahertz, 30 by 20 gigahertz. So this 6 and 4, this one is the uplink and this one is the downlink frequency. So this is in the C band region. This is the Ku band region. This is the Ka band region. More the frequency, severe the atmospheric effect. As you can see, the attenuation is going up along with the frequency. Rain attenuation increases roughly as square of frequency. So a satellite uplink operating at 30 gigahertz suffers 4 times as much attenuation as an uplink for at 14 gigahertz. Actually, when satellite communication started at the beginning stage of satellite communication, uh, not earlier days, but when satellite communication becomes very popular, they actually use this particular range of frequency, 6 by 4 gigahertz, but that means C band. There is a advantage of this C band. You know, atmosphere has got two major contributions. One is due to the troposphere, another is due to the ionosphere, right? For lower frequency range, ionospheric effect uh, is very crucial because they used to show huge amount of uh, perturbation or disturbances due to ionosphere. But in lower frequency range, tropospheric effect is negligibly small. Tropospheric effect includes rain, okay, rain, then turbulent weather, precipitation. All those things are actually concentrated on the tropospheric region. But C band is such a band that is in between the lower frequency range and higher frequency range. For higher frequency range, tropospheric effect predominates, whereas ionospheric effect has a negligible uh, contribution to the overall attenuation or disturbances. So C band was initially chosen as for this particular band, the tropospheric effect at the same time ionospheric effect both are lower. That is why this particular band was chosen. But later on, when it was found that 6 by 4 gigahertz is almost saturated, that means huge number of satellites are there in the sky, and interference started due to close spacing between two adjacent satellites. So the engineers have to think of some higher frequency range. At the same time, due to the high demand of bandwidth, we need to shift the frequency to higher values. So Ku band was chosen, and after that, this band 30 by 20 gigahertz band was chosen. But keeping in mind, these higher frequency bands are actually had adverse effect due to troposphere, not due to ionosphere. So different models should be used, rain attenuation model, then uh, different type of models are there. So all those models have to be used, and we have to understand the tropospheric effect before going to this 30 by 20 gigahertz or higher frequency ranges. So that is why it is said rain attenuation increases roughly as square of the frequency. So a satellite uplink operating at 30 gigahertz suffers 4 times as much attenuation as an uplink at 14 gigahertz. So for 14 gigahertz, the attenuation is comparatively lower, but for 30 gigahertz, the attenuation will be sufficiently high. Due to rain, all communication links are designed to meet certain performance objectives. Usually, a bit error rate or BER in a digital link or signal to noise ratio in an analog link measured in the baseband channel. The baseband channel is where an information carrying signal is generated or received. The baseband channel BER or S by N ratio is determined by the carrier to noise ratio at the input to the demodulator in the receiver. In most satellite communication applications, the C by N ratio at the demodulator input must be greater than 6 dB for the BER or SNR objective to be achieved. Those are the observed values. Digital links operating at C by N ratio below 10 dB must use error correction techniques to improve the BER delivered to the user. So I am just reading all those points. Analog links that was used in previous days, analog links using frequency modulation require wideband FM to achieve a large improvement in SNR relative to C by N ratio. The C by N ratio is calculated at the input of the receiver at the output terminals of the receiving antenna. RF noise received along with the signal and noise generated by the receiver are combined into an equivalent noise power at the input to the receiver, and a noiseless receiver model is used. In a noiseless receiver, the C by N ratio is constant at all points in the RF and IF chain. So the C by N ratio at the demodulator is equal to the C by N ratio at the receiver input. The overall C by N ratio at the earth station receiver depends on both up and down links, and both therefore must achieve the required performance for a specified percentage of time. Path attenuation in the Earth's atmosphere may become excessive in heavy rain, causing the C by N ratio to fall below the minimum permitted value, especially when higher range of frequency like 30 by 20 gigahertz or higher bands are used, leading to a link outage. Designing a satellite system therefore requires knowledge of the required performance of the uplink and downlink, the propagation characteristics, and rain attenuation for the frequency band being used at the earth station locations and the parameters of the satellite and the earth stations. So various things we have to study, and those things are actually useful for the design of the satellite link. Additional constraint may be imposed by the need to conserve RF bandwidth and to avoid interference with other users. Sometimes all of these informations is not available, and the designer must estimate values and produce tables of system performance based on assumed scenarios. It is usually impossible to design a complete satellite communication system at the first attempt. A trial design must be first tried and then refined until a workable compromise is achieved. So that is the common practice for the design of a satellite link.